Can we start the session, sir?
Yeah, sure.
Yeah, yeah.
No issue at all.
So I welcome you all in the second session of fourth day uh, on biomedical application of 3D printing by Dr. Y. Modi, sir. He is also my super senior, and it's my privilege to brief you, sir. Dr. Yashwant Kumar Modi obtained his Bachelor of Engineering degree from Shri GS Institute of Technology and Science, Indore, Madhya Pradesh. He completed Master of Engineering in Computer Integrated Manufacturing with honors in Computer Integrated Manufacturing. He obtained PhD degree in the area of additive manufacturing from JP University of Engineering Technology, JUET Guna. He has about 15 years teaching and 3 years industrial experience in various engineering institutions and industry as well. He served Institute of Management Studies, DAVV Indore, as visiting faculty. He has published many research articles and book chapters in reputed SCI and Scopus Index journals and books. He has delivered invited talks, lectures in reputed institutes and industries, including IIT BHU, Symbiosis University, Tata International Limited, and JP Cement. With this, I welcome you, sir, to start the session. Over to you, sir.
Thank you so much, Mayank, for this nice introduction, and very good afternoon to one and all present. I hope this session will be very helpful and learning experience for all of you. So I'm going to start my presentation now. Let me just share my screen. Okay. Okay, so Mayank, is my screen visible to
Yeah,
everyone?
yeah, perfectly
Okay.
visible, sir.
Okay, fine. So friends, I hope you have, I think you have attended almost 3-4 days of this FDP, particular FDP, and you must be aware about the basic fundamentals of the 3D printing process. So let me just share the agenda. Initially, I will be quickly going through the basic concepts of 3D printing in some 5 to 10 minutes, and then we will be moving on to state of the art in medical 3D printing. And next would be 3D bioprinting, the future of tailor-made tissues and organs. And then I will briefly discuss my own research work, which I have carried out at JP University, Guna. And lastly, there will be a question and answer session. So you all must be aware that what is 3D printing. That this is the subtractive manufacturing process we all are aware about. Okay, so in contrast to this particular technology, 3D printing technology is basically layer by layer technology, which we also can call bottom up approach. You know, in nature, most of the things are growing naturally. They are in additive in nature. Okay, so hopefully we have got this particular technology in manufacturing as well. And if we try to define this technology, then we can safely say that it is a group of manufacturing processes capable of fabricating a physical part directly from a CAD model by depositing material in layer by layer manner, as opposed to subtractive manufacturing processes. Let us see how a physical component can be realized from a CAD model. As we just discussed that at the initial point, we must have a CAD model with us. So initially, we must have a CAD model with us. But here I would like to say that we may have some other data as well, like we may have CT scan data, we may have MRI scan data or 3D scanners, data obtained from 3D scanners, or any other data that can be converted into faceted file formats. Any other data means, suppose we have our this digital elevation model, this terrain models, in if somehow we can convert that particular data, terrain data into STL format or some other file formats, faceted file formats. STL file format is basically one of the file format that 3D printing technology accepts basically, and it has become a de facto standard, industry standard. But other file formats are also there like VRML or PLY or AMF and many other formats that are acceptable to the 3D printing technology. So once we have a CAD model data, then we have to convert that particular data into some faceted file format. Okay. So as you can see on the screen, then we can convert, we have to convert that STL file into sliced model. And then one slice at a time is sent to any of the additive manufacturing machine. Okay. And then that gets fabricated layer by layer. And finally we obtain a physical component. And after this, there is a process called post processing. So post processing is something in most of the cases in with most of the 3D printing processes, post processing is required. Like it may have operation like sometimes we may have to clean the part. Okay, the some powder is sticked onto the part, so we have to clean that part. Sometimes we may have to paint it so that aesthetic appeal can be improved. Sometimes we may obtain some porous components, so in order to increase the mechanical property of that component, we may have to infiltrate that particular component with some other metal. So this type of operations are needed usually. So they are that is called post processing. Okay, so this is the process chain. Now, why this 3D printing technology? I am just using this additive manufacturing. I hope everyone is now aware about what is additive manufacturing, what is 3D printing, what is rapid prototyping, what is rapid tooling, what is this rapid manufacturing. These all words are usually synonymously used, but in 2010 itself, ASTM International has actually came up with the term additive manufacturing just to distinguish this particular technology from other manufacturing processes, because initially it was known as rapid prototyping, then it was called a rapid tooling depending on the end application. But additive manufacturing is a generic term, and that is more popular among in the technical domain, we can say, whereas 3D printing term is more common among the among common people as well as media and in medical domain. Okay, so but there is no much difference between all these terms, they may be synonymously used. Okay, and further detail if you want I can provide during the question and answer session. So why this 3D printing technology is becoming a big deal now? Because first thing is that the technological advancement has happened. Many technologies have grown significantly, and like CAD CAM technology has grown enough, and other technology has grown enough, so that this technology have become mature with the time. Nowadays, since inception in 1987 till date, the technology has grown significantly. Now it has become more capable. It can fabricate and use functional component directly. Okay, and then there is a growing range of printable materials, means the range of raw material has grown tremendously, and it is increasing day by day. There is a very great scope in material development for 3D printing processes. Okay, then freedom to operate due to patent expiration. Most of the initially launched technologies has already come out of the patent, like your 3D print, like 3D printing, binder jetting 3D printing, then FDM process, then stereolithography. These all have come out of the patents. So they are you may be seeing that growing number of these machines in market. And major industry and government investment. Nowadays government also focusing on 3D printing technologies. In fact, the Niti Aayog has launched a specific scheme for school children, that Atal Tinkering Lab. So government is trying to introduce this particular technology at the school level, so that they can make use of the hidden talent, and they can motivate the children to think dynamically and to tap out their creativity. So these are the some of the factors why we people are seeing that this technology is becoming very popular. And here are some strong features like fast prototyping. This is again, second is great design flexibility. This particular technology offers great design flexibility to us. Means flexibility, this we can say that complexity is nothing for this technology. How complex is matter? It doesn't matter. Okay, for this technology. Then there is multi-color and multi-material parts can be fabricated using this technology. Then no assembly required. For example, you can see a bearing here. We have to from if we produce this particular bearing using our conventional technology, then we have to fabricate the components separately, and then we have to assemble like race, poles, rollers, inner race, outer race, and assemble. In 3D printing technology, we have to prepare each individual components, individual parts, but we can make a assembly into the CAD model itself, into a CAD software itself, and then we can fabricate the entire component, entire assembly as a single component. So that is the biggest advantage of this technology. Another advantage is elimination of tooling. No physical tooling is used. And the mass customization. This is the, I think, the biggest advantage of this technology, because and this is particularly useful in medical domain also. Mass customization is a concept where you know getting getting things produced as per the person's requirement, as specific requirement, means we have to personalize the things. So that is very much possible using this technology. As you can see here, that the cost of the material does not increase with the complexity or customization with this 3D printing technology. Whereas in case of conventional technology, the cost goes up as soon as the complexity increases or customization increases. So that hurdle is not here. And finally, this particular technology supports the generative design. You may be aware about generative design. Nowadays, more and more companies, software companies, are coming out with this particular feature with their MCAT softwares. Like NXUG has incorporated a separate module for generative design. So just let me tell you what is generative design. In generative design, basically, we need not to create a entire CAD model. We have to feed the input data. Okay, what is the dimension of the component, what are the inner and outer various dimensions, as well as the load it can bear, or the material. This type of data we have to input into the software, and software using topologically optimized designs, it come up with several alternative designs, which we can then find out which one will be the best design. Like on the screen you can see that this is the component, and the software has actually designed the has presented this many alternatives. So we can go for this one, the last one, that is the with minimum material requirement, but at not cost of the strength will be at par with the first component, but weight will be reduced. So lightweighting components are very much important in as well as this aerospace is concerned, and medical and biomedical applications are concerned. So earlier you may be thinking that why this generative design was not earlier popular, because the manufacturing processes that were available were not compatible to produce such complex components. That's why they were not much popular. Okay. So I'm not going much into these categories of 7 categories. You may be aware about these technologies: wet photopolymerization, then binder jetting, then material extrusion, powder bed fusion, directed energy deposition. One or two I have left. Loam lamination, sheet lamination is there. Okay. So you may be aware about those technologies. So now we quickly move on to the application of 3D printing in medical and biomedical area. So, particularly, following areas from medical and biomedical field have been identified for the 3D printing process, where 3D printing process is applicable. The first domain may be, our first broad area may be medical anatomical model. Then the second area may be patient specific implants, then prosthetics and orthotics, customized tools and surgical guides, health monitoring and drug delivery devices, tissue engineering, and bioprinting. So these are the broad areas where 3D printing has got its applicability and becoming popular day by day. So let us see one by one. So first one is medical anatomical model. These medical anatomical models are mainly useful in education purpose, in education as well as for surgery planning and training. So what happens for education purpose, you may be aware that some anatomical models are used in school levels or in college levels or in medical colleges. So a student can be properly, trained on through train by train on these anatomical models, and they can be properly taught about the various parts of the human body. Okay, and then surgery planning is something where we will be seeing in detail. So traditionally, how these medical anatomical models are obtained. So there are mainly two ways in which we can obtain them. First, they are mainly made from foam. Foam anatomical models are available in market, as well as sometimes in medical colleges they are obtained from cadavers. But what is the problem with these models are very difficult and very expensive and difficult to obtain, because there may be a lack of cadavers, or sometimes you may not be able to get the body parts from cadaver. So there is a scarcity felt in medical colleges for this type of models. So 3D printing actually presents a perfect solution for this particular domain. Like in education purpose, you can see on a screen is a this lung, a model of 3D model of lung. So how uh, a student can understand the functioning of lungs, etc. Here is a spine. So they can, if they have a three-dimensional model of spine, then they can understand the mechanism of individual spine and how they are connected. They can very well understand the mechanism behind it. Here is a model of colorful model of heart. So then there is a model of femur bone. So this actually helps students. See, the virtual models are always available, but physical model of a specific patient may help understand students about the anatomy exactly and what is the organic shape of the particular body part. Okay, so this type of model help a lot. Like this is a skull model of a person, and then there is a model of foot. So this help actually foot model, they can understand that how many small bones are there in in a specific foot. Okay, so they can see the mechanism of the each and every bone and how they are connected, and what is the internal structure of a specific body part. They can really understand. Then comes the pre-surgical planning and training. So pre-surgical planning and training, basically, this type of model are basically used as a base for PSI, that is patient-specific implant and surgical guides. Then they may prove a tool for surgeon manufacturer communication, as well as they can be a tool to communicate between surgeon and patient. Okay, what happens sometimes? Suppose a doctor is to perform particular surgical surgery, then usually they can do. Usually they actually they have a virtual model CT scan or MRI scan, and they trace the problem, they identify the problem on the virtual model itself, and then they have to go for this surgery directly on the surgery table. Okay, so once they open the suppose heart or head, then only they come to know what is the problem and how it is. There may be significant difference between their observation and actuality. Okay, so nowadays how these anatomical models can be used, they can be used as a base for designing patient specific implants. Let me show you some pictures. Okay, so like you can see here, here is a skill, and this is lower jawbone. So entire jawbone is broken, suppose, and it is to be implanted. So doctors can get it scanned and can get a specific patient specific skull of the patient, and then they can design lower jawbone and they can fit it properly before the surgery actually takes place. So they can see the result whether it is fitting properly or not. So for this purpose, here is a case of mandible. Okay, mandible is broken, mandible, and they have designed a patient the implant fixing plate, we can say. And likewise, this is intramedullary fixation. So on the model itself, they can design some patient specific implants, so they can rest assured ki, okay, everything will go fine once the surgery is will start. And here is a cranial implant. And some other cases like here we can see, suppose brain surgery is considered to be very complex. So nowadays and it is in trend, okay, 3D printing, 3D printed models, patient specific 3D printing models are being practiced and studied by the doctors before going for actual surgery. So this is a specific case available on Google. So here they can see through MRI scan, they can obtain data, and then they have built this physical model, and then they can study the internal structure of the brain, and they can identify the location where they have to perform surgery, etc. So what happens, like a doctor, a specific doctor is not the only person who is a member of the surgery. There is a complete team. There will be a surgical staff or and a 2 3 doctors team. So they, what they really do in cases of complex surgery, they try to simulate the surgery beforehand, so that each and everyone involved in that particular surgery will be comfortable and already knowing that what is to be done at what particular time. So this is another case wherein two child are twin joint, we can say twin joint children are there, who are joined through their heads. So this was very complex surgery, and the doctors first 3D printed obtained 3D printed model of their head, joint head, and then they also prepared a model in soft material like silicon, so that they can perform the entire surgery on this. They performed, actually they performed the surgery on this particular model, soft model. So they are comfortable while they are going for actual surgery. And in fact, by performing this type of surgical planning and training, they have reduced actually the almost 25 to 30% of the surgery time. So that is becoming very popular nowadays for complex surgeries. And second domain is this patient specific implants. Till now we have seen that how models can help. Now this is another domain where patient specific implants are being made using this particular technology. So what is implant? Medical implants are devices or tissues that are placed inside or on the surface of the body. The surface of implants that contact the body is made of a biomedical material such as titanium, silicon, etc. There are many examples of implants like artificial pacemaker, cochlear implant, cranial implant, bone implant, stent, dental implant, etc. So what is the benefit of making these implants using 3D printing? Actually, 3D printing can help. The implants available in market are standard. It comes in standard size. So what a doctor has to do, sometimes if a particular fixation plate, suppose that is not correctly fitting to the anatomy of a specific patient, so they have made a cut on the operation table, and then they have to tailor that particular fixation plate to, so that that can fit properly onto the patient's femur bone, suppose. So that is the problem with the standard implant. And sometimes what happens, the standard, the organic, because the human body parts are have organic shapes, means free form shapes. So and these standard implants do not have these organic shapes, so the fitting has some problem. Once initially it fits well, but after some time, like in a span of 5 years or 10 years, when while some load occurs continuously on those plates, then they used to shift from its place. So that is the problem, and many times doctor advise to resurgery for that particular problem. So that are the problem with the standard implants, and the 3D printing actually helps in this. So like surgery is quick, easy, and safe. What are the benefit of patient specific implants? Means we can design a specific implant or implant as per the customer's body shape, body part shape. Okay, so surgery is quick, easy, and safe. So everything is planned before time. There, suppose femur bone fixation plate is to be made, so it will be conforming to the bone. So doctor is relieved, doctor is calm. Okay, this will fit definitely. Okay, then aesthetically superb results sometimes, because suppose just to have an example of this cranial implant. So earlier, suppose this type of cranial defect is there, then we may see people having some flat portion here. So there was no mechanism to exactly match the anatomical, yeah, organic shape of the skull. With the help of 3D printing technology, we can now exactly match the shape of the particular body part, so that results are aesthetically very correct. We cannot identify if some surgery has taken place at particular place. Next is reduced infection risk, because what happens if we are using patient specific implants, then the definitely the surgery time will be less. Surgery time will be less because no tailoring has to be done at the operation table, so that then reduced surgery time means reduced infection of risk. Then peace of mind means everything is pre-planned. Doctor already know, doctor know, patient know that everything will go away, so they will be really cool. And long term cost are lower. Long term cost are lower means once we have fitted it, then because they are properly fitting, their fitment will be conforming to the body shape, so there are less chances that they will displaced from their own place. So there is no need to resurgery. There are case studies where it has been found that patient specific implants have less number of resurgeries. Okay, so long term cost is lower in this case. Let us see some of the patient specific implants. You may not be aware that almost more than 90% of the hearing aids being produced worldwide are 3D printed only. Nowadays, most of the companies, almost more than 90% companies are using 3D printing technology for hearing aid. Then there may be different types of implants, like you can see hip socket uh, implant. Here is a load bearing bone implant. It can be used for a dental implant also, for making of denture or individual tooth can be made. Here is a case of a foot implant. This is made in titanium. So this was actually a case of a cancer patient. There was a cancer, bone cancer in his heel, patient's heel. So what the doctor did actually, doctor removed his heel, and they scanned the other heel of the other foot, and then believing that both the heels are similar, because they are in pairs, so they believe that both the heels are similar in design and in shape. So they scanned that, CT scanned that, and then they get it printed, and then they fix it into the cancerous bone. After removing the cancerous bone, so patient was well. So this type of implant can be made. Then here is a case of this cranial implant. This is material is PMMA, polymethyl methacrylate. So they can just scan. I'll tell you that how these implants are made actually. Uh, yes, in this particular slide, we will discuss how these implant and models, anatomical model as well as patient specific implants are made. So initially, we require a CT scan or MRI data of patient in a DICOM file format. DICOM file format is a medical specific file format, which is abbreviation for digital imaging and communication in medicine. So this particular file format contains the CT scan or MRI scan data of a patient. As I told you in the previous slide, in the first or second slide, that at the place of CAD data, we may have CT or MRI data. So that CT or MRI data has to be converted into some STL model. We have to convert that into STL model. Then that STL model can be processed, and we can directly make a model using that STL model. And then if we want to make a implant, specific implant, then we have to convert that STL model or that particular model into CAD model. Actually, STL model cannot be processed in our CAD modeling softwares. Those who are aware with the CAD modeling software, they know it very well that STL model cannot be manipulated or they cannot be edited. So we have to create a CAD model using that by fitting some nerve surfaces, etc. So uh, we have to create a CAD model, and then once a CAD model of the patient specific model is ready, then we can design a specific implant on that particular CAD model. So once we have designed a patient specific implant, then we can fabricate it using 3D printing technology. There are basically two ways. One may be direct way, or another may be indirect way. So in indirect way, we can go for rapid tooling approach. And in direct way, nowadays the technology has grown enough that we can directly fabricate the component either in metal or in ceramic or polymer. Whatever we want, we can make those implants using the latest technologies available in field of 3D printing. So this is how we can obtain a model, patient specific implants and model, and then we have to sterilize and then we can implant into patient's body. So let us see. Okay, this entire process is basically not that easy. Actually, we need to have a combination of doctors or radiologists and engineers, because we being engineer, we are not much aware about the medical area. And while we have to convert CT or MRI data into a CAD model, an expert radiologist is needed who can tell us precisely which particular segment is to be taken and which is to be left, which particular segment is related to the desired part and which is not desired. That can be known as a region of interest. So we have to identify with the help of a radiologist or a orthopedic surgeon may help us. So let us see this small video on this CT scan. So what is CT scan data basically? This is slightly different from our this X-rays. In X-ray, what happens? In X-ray, we have only a single image, whereas in case of CT scan, as you can see on the screen, that there is a machine and a patient is lie on a table, and then a X-ray beam scans the body of the patient by rotating around the body through 360 degrees. Okay, and it keeps taking the multiple images at different angles, and then all those images are sent to a computer system where different slices are generated. Okay, and those slices can be, if outer contour of those slices can be understood like a packet of bread. So there are multiple slices. In same way, there are multiple slices are at a particular axis of a patient. Okay, there may be less or more number depending on the thickness of the layer of the patient. So just see this video first. So here you can see how the X-ray is rotating around the patient body, and there is a X-ray detector that keeps detecting the X-ray and taking images of at different angles, and then it is sent to the computer, which basically separates them and makes different slices. Okay, so here you can see 5 chest CT scan and 1 chest CT scan. As I was talking about, that the thickness of layer is more, then less number of layers will be there. Otherwise more number of layer, more will be the number of layer. In case of we will be getting better accuracy. Okay, so this is how CT scan data behaves. You will find some 100 or 200 or even 500 or 1000 images in a particular CT scan data, and what usually doctor gives us is actually only 5-10 images. Okay, so if we can have a soft copy of CT scan, then we will be able to see those images. And while converting the CT scan data into a virtual 3D model, we need to apply Hounsfield units for CT scan. Actually, what happens? This indicates the density. This is depending on the density of the body part. X-ray actually tries to go through the body part. So some of the body part absorb the X-ray, and sometimes it pass through. Okay, so depending on that, Hounsfield has devised some density number. This is unitless number. So air has minus 1000 Hounsfield units, lungs has minus 700 to minus 850, then water has 0, and this cancellous bone and cortical bone. Cancellous and cortical bones are the outer and inner. Outer portion of our bones are known as cortical or hard bones, and inner portion is known as cancellous bone, that is also known as soft bone. Fine, so they have 300 to 400 and 800 to 200. Actually, for converting this CT scan data into a virtual model, we need certain softwares like I'll name this. In some open softwares are available like Invasilis and DWide. These are the open source softwares, and there are commercial softwares like Mimics or this 3D Doctor, where we can convert this CT scan data into 3D model. And here is the how CT scan data while loaded into a DICOM viewer. Doctors usually use this type of DICOM viewers. There are free DICOM viewers available on internet. You can go for that, and we can see once in the file a specific CT scan or MRI file is uploaded, we can scroll through the different slices. Suppose 100 slices are there, so it is showing, it is suppose moving from bottom to up, so it is showing the cross section at a particular slice. Okay, and doctor can identify this very easily. Then while this CT scan data, two-dimensional images are converted into three-dimensional image, then it looks something like that. That can also be viewed in a DICOM viewer, and by removing unnecessary data or noise, we can have a virtual model. Okay, so that particular model can be stored in STL file or any other faceted file depending on the software. So once we have stored this virtual CAD, not CAD model, virtual model, 3D model into STL file, then that can be printed using any 3D printer. But that will be only for printing purpose. That will give you a CAD model of the part. We cannot design any implant on that this particular data. Okay. Okay, this is another MRI image while loaded into DICOM viewer. It looks like this. It shows cross section at different height. Okay, so this is about these implants. I hope this would be clear. I was just telling you that this particular 3D model can be converted into STL file that can be directly given to STA and directly given to 3D printing machine, and that can make our model. But we cannot design our implant on this particular CAD model, because being an STL model, we cannot make an implant. We have to convert that further into a CAD model. Okay. So next domain is prosthetics and orthotics. This is another area where 3D printing is finding its application. So prosthetics are basically devices that replace a missing body part, whereas orthotics are the devices that are used to modify the structural and functional characteristics of the neuromuscular and skeletal system. Means simply we can understand that orthotics are something which supports a existing body part. Body part is not missing exactly. We suppose we have some heel problem, heel bone problem. So doctor advise us to put some silicone gel material and the sole at the in the shoe, so that it can relieve our pain. So that is a sort of orthotic. Whereas prosthetics is something which is used to replace a completely missing body part. Suppose a lower limb is missing, or due to some accident a patient has lost his lower limb, and then we have used a artificial limb, then that is called prosthetic. So in this particular domain also 3D printing has got a very good scope. Almost all the processes which you might have studied so far, like stereolithography, or whether it is FDM or selective laser sintering, these all are capable of producing prosthetic sockets, and many companies are have started producing such sockets nowadays. So what is the traditional method of making prosthesis? So traditional method of making prosthetics is very time consuming actually. Patient has to visit the clinic, and then doctor with the help of plaster of Paris material and some canvas, they he makes a positive mold of the remaining stump of the patient. Here you can see they have made a stump, and then through this positive mold, the negative mold, they used to make a positive mold, and then again that stump is used, stump mold is used for making of the socket. Okay, so from positive to negative, negative to positive again, and then they make create a socket by thermoforming process. Usually thermoforming process is used for making of socket. So basically these conventional techniques is time consuming, and it has certain problems or disadvantages as well. A patient has to visit multiple times, and it may result in dry and scaly skin, or sometimes risk of ulceration and infection may be there due to the humidity and all this. So this is somewhat not preferred process. So instead of this particular process, the modern approach or the latest approach is using 3D scanning. I also mentioned in second slide that instead of CAD model, we may have 3D scanner data. So 3D scanners are basically used to scan our body part. There are different types of scanners available in market. Okay, laser scanner may be there, white light, scattered light scanner, light scanner may be there. Different scanners are there. So doctor usually what do? They scan our affected body part, and then they try to make a CAD model using that particular data. So using 3D scanner, we usually have a point cloud data, and that point cloud data has to be converted into some sort of geometry, because that is not a geometry actually. They are scattered point, only cloud of data, points, cloud of points. So that has to be, we have to fit, we have to apply certain process like image segmentation. Uh, the desired portion is to be remained, and unwanted portion is to be deleted. Then we have to fit some nerves so that we can create a surface through those data points, and then using that surface we have to create a solid model. So once we have obtained a CAD model, then there is no problem. We can have we can get it 3D printed using any of the suitable technology. Okay, so this is the approach that is being used nowadays. And here are some of the examples of customized prosthetics and orthotics. Here you can see foot orthosis, and this is ankle foot orthosis. Depending on the different type of um, disease or problems, doctor advise different types of orthotics, or sometimes they may have to go for prosthetics. Okay, so here you can see this is custom made leg immobilization splint, and there may be some injury in the leg, so leg should not be mobilized. There should not be any mobilization, so immobilization splints is there. This is a wrist orthosis, wrist immobilization splint. And here you can see this is customized procedure designed to minimize prosthetic scanned the stump, remaining stump of the leg, and then they have converted the data into CAD model. And once CAD model is obtained, that can be printed using any of the process, and then pylon etc. can be fitted here, and a artificial limb can be prepared. And here is another example for this customized prosthetic orthotics. This is exoskeleton. This woman especially has a very severe injury in spine, so she was not able to even stand up. And then with the help of FDM technology, this exoskeleton system was developed, and she was able to move. Okay, so such applications are there. How much time is there? Okay, 120. So next, am I audible to everyone? Because I'm not able to see any one of you. I'm presenting my screen.
Audible, sir, is.
Okay. I'm just continuing.
Voice is clear, sir.
So next domain is tissue engineering. So what is tissue engineering? Tissue engineering is an interdisciplinary field that applies the principles of engineering and life sciences towards the development of biological substitute that restore, maintain, or improve tissue function or a whole organ. So basically what tissue engineering does, we have to extract here with this figure we can understand this very well. We have to initially, there is, suppose there is a patient, and then we have to extract the cells from this particular patient specific cells have to extract it, and then they have to be expanded, they have to be multiplied cells in laboratory. Then those cells are seeded onto some structure. This structure is known as scaffold. So they are seeded onto this particular structure, and then they are allowed to grow further with the help of some growth factors and in controlled environment in laboratory. And once they are grown enough, they are sufficiently grown, then they are implanted into person's body. So this is something called tissue engineering approach and regenerative medicines. Okay, so basically the role of 3D printing is limited to this scaffold manufacturing. This scaffold is basically very important part of this entire process. And there have been traditional processes for manufacturing of this scaffold, like salt leaching or um, foaming processes, but they have their certain limitations, like they cannot they do not have a specific control over the microstructure and macrostructure of the pores. I'll talk a little later. Okay, here also I'll be talking about this. What are the properties an scaffold must possess? It must be biocompatible first of all. Biocompatible means it should not react with the body or body fluid or blood or anything else. It should not have any negative effect, any poisonous effect with the body. Then it should be biodegradable. It need not be biodegradable, but it may be biodegradable. Suppose we have a metal implant, then it may not be biodegradable, but sometimes biodegradability is required, sometimes it may not be required. We will see in later slides. Then it must have adequate porosity. Porosity is very important. Then adequate mechanical strength and surface topography and chemistry. So let us talk something about this particular thing, porosity. Why porosity is important? Actually, this is the primary need of this scaffold. It must carry sufficient open porosity. Basically, means there must be interconnected pores. Pores should not be closed inside it. There must be through porosity, so that the cells which we have seeded onto them, they can grow, they can proliferate properly, and they can survive there. So adequate porosity must be there, and simultaneously the scaffold must have adequate mechanical strength. So these two objectives are basically contradictory and have very research potential in fact, and many researchers are working on this particular domain, that they are trying to balance the porosity, and as well they are trying to set up a balance between porosity and mechanical strength. Because what happens, these scaffolds may be used in two ways. There is a term something known as in vitro and in vivo. So in vitro is something which is done inside a laboratory, whereas in vivo is something which happens inside the human body. So if we want to have a scaffold that can be directly implanted inside the human body, then it must carry adequate strength so that it can bear the load of the human body. Okay, and uh, in case of in vitro, the mechanical strength is not that much important. It must only have the mechanical strength that can bear the load of the cells, etc. While cells are growing, it should not break down. So these are the properties of the scaffold. Then proper surface topography and chemistry must be there. Means no cytotoxicity should be there. Means the cells which are growing on the surface of the body should remain alive. They should not die down. Okay. So these are the properties a scaffold must have. And why 3D printed scaffold? So as I told you, that traditional processes are also available, but still 3D printing, why 3D printing printed scaffolds are being used? Because first thing I have already discussed, they have 3D printing has a very good control over the macro porosity. We can design in our CAD software different types of porosity are interconnected channels into a CAD model, and then we can get them printed. And customized shapes are difficult to produce using the traditional processes. That is very much possible using the 3D printing. As you can see, this mandible can be we can have a CT scan data, as I have already explained, and then we can get it its CAD model data, and then we can modify it according to our needs. What is the porosity? You can see porosity here, porous structure. So specific shapes can be given using 3D printing technology. Like this is ear, outer ear. So what happens? This particular thing is again, I think, mandible, and this patch has been designed 3D printing. Okay, so suppose this ear shape, we have scanned the ear of a specific patient, and then we can make its CAD model, a porous CAD model, and then that can be used for tissue engineering. We can seed the cells. Particularly stem cells are usually required in this. So stem cells are seeded onto this particular thing, and then they are allowed to grow. And then once they are fully grown, and when it develops properly, then it can be implanted into the human body. Okay, so another domain into tissue engineering. Bones, although they are self-healing abilities, but in case of critical or complex cases, we may have to go for bone graft procedures. Okay, so bones are basically osteogenic, osteoconductive, and osteoinductive. What these things are? Osteogenic means they have they have bone forming cells in them. Osteoconductive means they have capability to conduct the cells from one inside the structure, and then osteoinduction means they have the capability to promote and proliferate those cells. So these three properties are there in bones, so that they have the self-healing abilities. So if bone grafting is basically two types of bone graftings are popular nowadays: autograft and allograft. In case of autograft, patients his own bone are used, that is removed, and it is placed somewhere else. In allograft, some donor is identified and then it is obtained. Whereas in case of synthetic, in the cases where this both the procedures are not applicable, due to some reason, then we can go for synthetic composite graft developed using bone tissue engineering. And this type of scaffolds can be developed using the 3D printing process. Just see this video. So with the help of this robot, this cancerous bone is removed from the patient's body, and then it is scanned, 3D scanned, and a CAD model is prepared using this particular piece, and that CAD model is used for 3D printing, and exact piece has been made using 3D printing technology, and that is placed at this particular cavity. This is what I was talking about, topologically optimized design. Using traditional process, it is very difficult. So in this way, this technology is being used. Okay, this is a patient specific load bearing bone of femur piece. A particular it will fit between a cavity on femur bone. Okay, then there is area customized tools and surgical guides. This technology is being used for manufacturing of customized tools, customized surgery tools, and customized guides also. You can see here a denture guides drilling purpose. For drilling purpose, this guide is there. This plastic transparent guide. First, the model of denture is made, and then for that denture model, a guide, surgical guide is. Just a minute. So the surgical guide is there that can be used for drilling purpose. Here also some guides are manufactured. Okay, so the next domain is health monitoring and drug delivery devices. Using 3D printing, doctors can design customized drug doses. They can print tablets with particular dose, and there are certain other applications like electronic drug device delivery system. This is a electronic drug delivery system, so that can, depending on the situation of the patient, this data is there, sensors are there, microcontrollers is fitted, so this can release the calculated amount of drug in patient's body. Sometimes ingestible devices are also being manufactured. And just let me go to this. Another advantage of additive manufacturing is the ability to make complex micro devices that work inside the body to deliver medicine or to monitor a patient's health. An ingestible device that can remain in stomach for a month, self-powered, it delivers discrete amount of drug for patient requiring long-term care, such as the treatment of cancer or HIV. So this is the devices. This is in development process. They are just trying the possibility. Such micro devices will soon be able to transmit data wirelessly to an external medical wearable for detailed health monitoring. So these are the application in health monitoring. And the next part is bioprinting. So we know that thousands of patients are waiting for many types of organ transplants worldwide. Okay, and many of them die every year due to non-availability of suitable organs. And bioprinting may prove a boon for such patients. Bioprinting is actually one stage ahead from the 3D printing. In case of 3D printing, we basically use an engineering material, whereas in case of bioprinting, we use biomaterial. Especially, it is given a name bioink. It use bioink for printing the organs or tissues, human tissues. So what is bioink? Bioink is basically a blending of stem cells. So initially stem cells are extracted from a patient, and then some growth factors are added, and hydrogels such as alginate, gelatin, etc. are combined with this, and a bioink is prepared. Okay, so major role is of stem cells in this particular case. So what are the stem cells? Stem cells are the foundation of every organ and tissue in our body. Stem cells are undifferentiated cells that can turn into specific cells and the body needs them. Okay. All stem cells can self-renew and differentiable means we can say that the stem cells are the smallest building block of our human body. So they are actually not specific cells, they are general cells that can be converted into any of the specific cells. Okay, that's why stem cells are in so much we are paying so much attention nowadays on stem cells. Okay, there may be different types of stem cells like embryonic stem cells, adult tissue cells, mesenchymal stem cells, induced pluripotent stem cells. So let us have very embryonic stem cells usually found obtained from embryo, the fetus or the umbilical cord. And that's why many people used to preserve their umbilical cord at the birth time. Okay. So then adult stem cells may be obtained from an adult person's brain, bone marrow or blood vessels. But their number is very few, means they are very difficult to obtain from a human adult human being. Then mesenchymal stem cells, they are obtained from connective tissues or stroma that surrounds the body, organ and other tissues. Scientists have used MSCs to create new body tissues such as bone, cartilage and fat cells. And another type of cells is IPS cells. They are actually prepared in laboratories. Okay, so scientists have developed many types of cells in laboratories. Okay, so these type of stem cells are used at the initial point. Now let us see how bioprinting works. So bioprinting is an extension of 3D printing that make use of cells, growth factor and biomaterial to print biomimetic tissues, bone, blood vessel and even whole organ in layer by layer manner. So initially a bioink is required. A bioink is okay. So bioink means it use traditional type of printer. Although the printers manufacture wise they are different, but principle wise they are same. Basically, three types of printers are used for this purpose: extrusion based. Next slide. Extrusion based, then inkjet based, and laser assisted bioprinting. Bioprinters. Three types of bioprinters are more popular nowadays, and so initially what happens, the one layer of bio ink is sprayed onto or deposited onto the substrate, and then there is a layer of bio paper or something called bio hydrogel, and then next layer is deposited, the next layer is deposited. In same way as 3D printing works, only the difference of the material. So here material is bio ink. So finally since the this bio ink is blended with the growth factors and hydrogel, so they help them grow. They are kept into bioreactors and allowed for growth purpose. While they are matured enough, they've grown into inside the bioreactor, then they become a final living tissue, and then they become transferable, transplantable into the patient's body. So this type of research is already in progress, and this I have already spoken about. These three types of bioprinters are nowadays in practice. So latest developments in this particular area: San Diego based Organova, the first commercial bioprinter company, has tried printing skin tissues, heart tissues and blood vessels among other basic tissues. A research team at Swansea University, UK, has developed soft tissue and artificial bone for eventual use in reconstructive surgery. Another research team at Wake Forest Institute of Regenerative Medicine created functional artificial bladder and kidney. Research group at University of Pennsylvania tried creating vascular network using sugar template. Sugar template was dissolved once network was fully grown. So the major issue in this particular domain is vascularity. As mentioned here, the scientists and researchers are trying to obtain vascularity. Let me tell you what is vascularity. In fact, in human tissues, what happens? There are tiny pores are there which are used for transportation of these nutrients and oxygen. Okay, so scientists and researchers are trying to create those vascularity, they're trying to impart that type of vascularity into the fabricated organs. Okay, and they have succeeded up to some certain extent, but still there are many challenges in this particular domain. That resolution and speed of the process is still need to be improved. Bioink viscosity is also a challenge for the researchers. Then limited range of biomaterial is there nowadays. Choice of vasculature, this I was talking about, and then expensive in comparison with regular organ transplant and ethical issues. So these ethical issues is very prominent in this particular area. Not only this particular area, even in 3D medical 3D printing as well. The ethical issues are still exists, and there need to be there need to have a specific ethical and as well as legal guidelines for printing up specific implants and implanting those implants into human body. So that is again a challenge, and there are certain biocompatible materials, and this is a list of biocompatible material. I hope it has been covered in the material portion. And then I'll quickly go through the research that is going on in JP University. In JP University, we do have actually two of the 3D printing machines, YASHWANT P395. This machine is imported basically from Germany. This is the AM lab of at JP University. This particular machine is YASHWANT P395. This is a selective laser sintering machine, and raw material used in this process is polyamide, and this is very costly actually commercial machine, and is costing around 2 crore. And the second printer is this one is the jet printer 450 is also there. This has the capability to print full color components. As you can see here, the components have been printed using this YASHWANT P395 machine, and these components have been printed using their jet printer 450. Apart from this, many softwares like Magix RP, RP Tools, JEdit, JetPrint, Creo Element, SolidWorks, Abacus are available in our laboratory, additive manufacturing lab. And here are some of the work which I have carried out. We have tried a cranial implant, and we have successfully made this cranial implant. I have also published one paper on this SCI publication. And so initially we have to CT scan. We need to have a CT scan data. Then certain softwares are to be used. In fact, for this particular project, we have also used a Geomagic freeform software for CAD modeling, etc. And then we have designed this particular cranial implant, and these are the fabricated models of the implant as well as skull. Then second is pelvic bone implant. We have fabricated this. Again, used same software, and here is the pelvic. This is polyamide material. Then there is a calcium sulfate based porous bone scaffold. Actually, we are also working on this particular project on this porous bone tissue engineering. So we have actually we have developed a certain bone scaffolds, porous bone scaffold of calcium sulfate material, and with different porosities. Using the Z printer 450, the material used in this is ceramic material basically, and we have developed, because here as I told you that objective is multifold, And contrast two contrasting objectives are there, that porosity should be more, as well as the strength or mechanical strength should also be more. So if porosity goes high, then definitely the strength will come down. So we need to have a trade-off between this porosity and strength. So I have also published one research paper on this particular work. Then we also got it CT scanned on RRCAT, and to just check if raw material or the raw powder is completely removed from the pores of the scaffold or not. And then we also gone for this cytotoxicity test. Here you can see this model of scaffold. So these are the results after 24 hours and 36 hours. So we could see the many of the cells. Those cells were did not die completely. So it concluded that the this particular method is successful in manufacturing of porous bone scaffolds, as well as it does not have much cytotoxic effects on the cells. And another study that we went for this wrist splint. Initially, we obtained a point cloud data through scanning, 3D scanning. Then we developed a CAD model using that. And after developing a CAD model, and we apply certain offsetting, etc., to accommodate the cushion between the wrist splint and the hand. Then we split it and apply certain recesses there, and this pins for this velcro, etc. And then finally we printed this one. So these are some of the research work took place here in JJ laboratory. With this, I am just closing this particular presentation, and these are my contact number and email ID. And these are the bibliography. I have used many pictures from internet, so I'm just giving a credit to those things. Thanks a lot. Thank you so much for your patient hearing.
Thank you so much for your nice presentation, sir. I request participants, you can start asking the questions. If you have any doubt or query, you can ask.
Sir, very good afternoon. This is Anthony from Chennai, sir.
Good afternoon. Good afternoon.
Sir, what kind of material it is suitable for making wrist material, say for epoxy
For wrist splint,
polymers or etc.?
for wrist splint, you are asking about wrist splints.
Yes, sir.
For wrist splint, usually polyamide is used. Polymer material is used.
Yeah, for medical purposes. What kind of?
Yes. Medical purposes, there are medical grade polymer are available, like PMMA, or polyamide. This polyamide 2200 from US is also medical grade polymer. Okay, that is the nylon 12 based material. So there are many biomaterials available, biopolymer are available that can be used for this particular purpose. And the technology that can be used for this is FDM, stereolithography, and the selective laser sintering. They may be very well used for this particular purpose. You can check the manufacturer's site. They have many biomaterials available with them, and they also mention that with which particular system you can use that particular material. So biomaterial, any polymer can be used for this particular purpose.
Thank you, sir. Thank you. Thank you, sir.
Thank you so much.
You can also ask in chat box. Sir, there is one question in chat box from Venkataramana.
Okay, I'm just checking it out. Uh, Generally, we have CAD model and then STL file. How to get the CAD model from STL? I think STD, it is STL. Okay.
Yeah, yeah.
How to get the CAD model from STD? Not actually STD. We have to, what I have told you, that initially when we convert CAD data, CT scan data, then we obtain a particular CAD model. Okay. We obtain particular 3D model that we have to bring into the CAD modeling software, and we have to actually reverse engineer that data. Even it is STL data, or even it is mesh data. Actually, we have to save into it mesh data, and in mesh data we have to fit a curve. By fitting curve, or nowadays automatic process is also available. So using those processes, we have to that also fit the curves onto the mesh data, and then they generate a surface onto that particular data. And once the surface is generated, then we have to develop a CAD model by offsetting or something like that. That is to be done. Because through point cloud data or CT scan data, we cannot have directly CAD model or CAD data. Okay, that data we can only convert it into mesh data, and through mesh data we have to convert that data into CAD model. Means it must have certain geometry, because CAD is a geometry driven geometric modeling. So so the data which is obtained from their CT scan or MRI scan, that is not a geometry driven data. So we have to fit the this curve, etc., and we have to convert that into geometry driven data.
Okay, sir. Sir, my question is that as
Yes.
we find a .stl file in Thingiverse and any other GrabCAD or some websites or links just to
Mhm.
convert it into for the 3D printing. So
Mhm.
how can we find, sir, this DICOM file to learn about medical 3D printing?
Yeah, that is nice question actually. In order to find the DICOM data, you have to contact any of the hospital first. Okay, at first place. Sometimes what happens if you are not in contact with any of the hospital and you just want to want this data for practice purpose, then you can also find it on internet. There are certain sites there you can find free DICOM data. I'll share some of these sites with you on mail. So there are if you will search on internet, then you will find some sample data, some sample DICOM data on internet, so that you can use.
Okay, sir. Okay, sir.
Mhm. But just let me tell you that converting that DICOM data into CAD model is not that straightforward. It is very
Okay.
tricky, and it certain sometimes it requires different softwares. Like we initially we tried SolidWorks, but we could not convert it. Then we tried CATIA, we could not do it. Then we have to use Geomagic Freeform. So it is very tricky. But nowadays commercial softwares are available, like 3matic from the Mimics only. Mimics and 3matic are the two software. So 3matic takes care of this CAD modeling part, and Mimics takes care of other things like medical modeling, etc. So specialized softwares, but they are a little costly. So if we can go for certain free softwares like Blenders or um, like Mesh Lab or other softwares are like nowadays Fusion 360 is also educational version is available. So you can try any of the software uh, for conversion purpose.
Okay. Thank you, sir. Thank you.
Any other question?
Yeah, this is last call. If any participants want to ask, please ask. Okay, sir. So with this, I would like to thank you, sir, for your valuable time and support to give this lecture on behalf of Mechanical Engineering IPS Academy. I would like to thank you, sir.
I would also like to extend my heartfelt thanks to the management of IPS Academy, the Professor Sanjay Jain sir, and yourself for
Yeah.
inviting me to deliver my viewpoints on this medical application of 3D printing technology. Thank you so much. Thank you one and all present for your patient hearing. I hope this will prove a very learning experience for you as well
Yeah,
as.
sure, sure, sir.
So thank you so much once again for inviting me.
Thank you, sir.
Thank you.
Thank you all the participants to be here. We will start the next session by 2:30 on materials for 3D printing, various materials though which are used for the 3D printing by Mr. Hemendra Patil, sir. So we will meet at 2:30. Thank you. Thank you for patience listening.